So, let us have a quick check on what we have discussed in our last class. So, we talk about the potential, and there I told you that instead of defining potential at a particular point, we define the potential difference. So, it is actually a difference. So, potential difference. So, in a field, how potential difference between 2 points is defined? When you are moving a test charge q naught from one point in a space to another point, then whatever is the work done by external agent per unit test charge, that is defined as the potential difference between the 2 points in a space. So, dV is equal to work done by the external agent per unit test charge. Either we can use this definition, but here this work is when there is no change in kinetic energy. So, without any change in kinetic energy, if you are doing work per unit test charge, then we will get the potential difference between 2 points. I can also use another definition like change in potential energy per unit test charge when we are moving q naught test charge from one point in a space to another point, then this will give me potential difference between 2 points, right. And using these definition, we establish the relation between potential difference and the electric field in the space, right. So, dV came minus E dot dr, right. So, there are two ways of expressing the field in a space. One is a scalar way, another is a vector way. A scalar way is the potential, and the vector way is electric field, right. So, this was the relation we got between potential difference and the electric field in the space, right. And then we solved some problem based on this one. And I told you that if field is given, if this is given, to find out the potential difference you need to integrate, right. Similarly, if potential is given and you want to find out field in a space, then the procedure is differentiate potential with respect to x partially, put I cap, then differentiate potential with respect to y, put j cap, and differentiate potential with respect to z partially and put k cap. So, this way you can find out electric field in vector form. If potential is given, you can find out field. If field is given, this is the way to find out potential in a space. Here you can see that I am writing dV, that means here it is the difference between 2 points, right. Let us see few more example related to these two expression what we have derived using the basic definition. Let us see simple numerical first. So, electric potential in a region is represented by V is equal to 2x plus 3y minus z, and question is find the field expression in space, right. As field is a vector quantity, we need to express it in vector form, and just now we have seen that E is equal to minus of differentiation of V with respect to x partially, then with respect to y partially and z partially, right. So, if I substitute this one here, what is the first term I am going to get? As we are doing differentiation partially with respect to x, y and z are to be considered as constant. So, differentiation of constant will become 0. So, differentiation of these two terms will be 0, we need to differentiate this 2x. So when we differentiate 2x, 2 I can take out, x to the power 1 differentiation is 1. So I am now directly writing, when you differentiate this one with respect to x, these two will be 0 and differentiation of this one will be 2, then I cap plus. Now I want to differentiate with respect to y. So if I want to differentiate with respect to y, I need to consider x and z constant, partial differentiation. If I consider x and z constant, differentiating the whole expression with respect to y will give me 3j cap plus. Look at the last one. With respect to z, now we need to differentiate. So to differentiate with respect to z, now these two are constant and differentiation of z to the power 1 is 1 with minus sign, here minus 1 k cap. As our field does not contain any xyz term, this comes under category of uniform field. So this is a uniform field. Uniform field, right? So irrespective of the location in a space, whether 0, 0, 1, 0, 2 or any other point, everywhere field will be like this, right? I hope application of this formula is clear. Let us see another example. Find the potential due to field at x, y, x comma y if the potential at origin is 0. So reference is given to you, this is reference. So giving reference, I can ask potential at a point in a space, but if no reference is given, I cannot ask potential, then question will be something related to the difference. So question might be find the potential difference between these 2 points, right. Here as reference is given, I can ask potential at any general point x comma y. Now, so field is given and we need to find out potential. Expression is dV is equal to minus E dot dr. Right. So if I substitute this one here, then I will get minus, take minus out, integration 2axy I cap x square minus y square j cap dot dr vector will be dxi plus dyj plus dzk. So if you do dot product, we know that I dot I is 1, j dot j is 1 and any other combination I dot j, j dot I or k dot j, all those will be 0. So ultimately you are going to get this product and this product. So I can write minus in bracket integration look at this one, this dot product I dot I 1, so this will become 2 axy dx, first term. Look at the second one, plus this dot product ax square minus y square dy. So you can see that this term contains only y and I can take this term out and can write this as 2axy dx plus ax square dy minus ay square dy, right. Now the problem here is this term contains y and we cannot integrate this one with respect to x unless until we know the relation between x and y. Same happens with the next one. Here x square is coming, but there we have dy. Again you cannot integrate this term unless you have the relation between x and y. There is no problem in integrating this one because this is y square and it need to be integrated with respect to y. But nothing is said about the path and all, right. As this is a conservative field, obviously if I am asking potential, then field has to be conservative, right. So I can convert this into direct function form. That means I can also write it this way, these two as one term, integration this as another term, right. So I combined that x square dy with this one and this I can convert into direct function form. How? Let us see. So if you look at this one, this can be written a times differentiation of x square y minus now this term ay square dy integration. I hope you are understanding what I am writing. So fx into gx form. So if we have something fx into gx form and I am differentiating it, then it is nothing but gx d of fx plus fx d of gx. In differentiation you must have learned that any function in this form can be written in this way. Similarly this thing can be written this way, because if you open this one, see if I differentiate. So first I will differentiate x square taking y out, I will differentiate x square. So that I will write 2x dx plus the next term. Now I will differentiate y keeping x square as it is. So keeping x square as it is, I am differentiating y, then I will get this, and in front of that we have a in multiplication. So a will appear here and a will appear here. Now see 2a xy dx 2a xy dx ax square dy ax square dy. So differentiation of this term will be this way. So I can convert this one into this one. I hope this one is clear. So whenever field is given and potential is being asked, you can always convert these terms into a single term. Now there is no problem in integrating this one. Integration of d of z is z only. So if I integrate this one, d of x square y, integration of this one will give me x square y only, right. Now let us put the limit. So using this concept, I converted this term into this term. Now comes limit. So we can use the reference given in limit. This is negative of that, right, minus here also, this is minus minus, and here outside minus, I will keep minus here, is equal to dv integration, right. and limit is what? At origin potential is 0. So 0 comma 0, there is no z term, that is why I am writing only 0 comma 0. If there would be z term, I will be writing 0 comma 0 comma 0. Potential is 0. What would be the potential at x comma y? Now see, here if I integrate, I will get v minus 0 minus this. If I integrate, this is a, and integration of this one will give me d of this, d of z, integration will give you z only. So I will get only this upper limit minus lower limit. So x square y minus, when I put 0 here, this whole term will be 0. First term over, minus next term a y square dy. So integration of y square is y cube by 3, upper limit minus lower limit. Here we have limit of y only, no x term is coming. So this can be written y cube by 3 minus 0. So potential what we are getting, V is equal to minus ax square y, right, this minus and this minus will become plus y cube by 3. So field is given in space and potential is asked. This is the procedure. So this was the formula what we used. So in our last class we talked about this formula, we did some numerical based on this formula. Today also we have taken few more numerical to make the concept crystal clear. Now let us move to next topic. So we have just defined the potential. Now let us see what would be the potential due to different charge distribution. So first we will see that what is the potential due to a single point charge, and using that result we will get the potential produced by different charge distribution like ring, disc, hollow sphere, solid sphere, sheet, wire, all that can be done using the result what we are going to derive for point charge. So let us take point charge. So potential due to a point charge. So because of this charge say Q, I want to find out potential at distance r, right, and I can use the definition that if I move this charge from this location to that location, whatever be the change in potential per unit test charge, that will give me potential at that particular point, right, or that will give me the potential difference between this point and infinity. So what I am doing is, keeping this charge fixed, I am moving this test charge towards infinity. So according to the definition, we have potential difference between r and infinity is change in the potential energy when you are moving test charge from r to infinity per unit test charge, and this we take as reference, this is 0, and this potential energy associated with this system at this particular moment is K Q naught divided by R. So I will substitute this value here. You can see this Q naught and this Q naught will go, and finally you will get potential at distance r from point charge is 4 pi epsilon naught r. K is equal to 4 pi epsilon naught r. So from this charge at distance r, potential is defined as Q divided by 4 pi epsilon naught r. So we use the basic definition to get the expression of potential at that particular point. Now as I already told you, that for potential energy, as that is a scalar quantity, potential energy as that is a scalar quantity, you have to substitute charge with sign, right. So if our charge is positive, I write positive here, if charge is negative, I write negative here. Same thing happens for potential. Potential K Q divided by R, this is what we are getting. So here charge must be with sign. That means if our charge is negative, potential will start from minus infinity, and as you keep going till infinity, it reduces to 0. If our charge is positive, then potential very near to the charge will be plus infinity, and as you keep going, it reduces to 0. If I assume that this is say 1 microcoulomb, assume that somewhere here you are getting potential 100 volt, unit of potential is volt, right, or I can also write joule per coulomb, or I can also write dV is equal to minus E dot dr if I use this definition. E is equal to F by Q. So from here I can have the unit that Newton per coulomb into meter. So Newton meter per coulomb or joule per coulomb, or it is also expressed in voltage, volt, right. So assume very near to this one, this is 10 volt, if you just move by some distance you will get 25 volt, then you move certain distance you will get 25, from 50 it reduces to 25, as you keep going away then it reduces, and finally at infinity it will become 0, right. If our charge is negative, so then what will happen, here somewhere near to this one you will get minus 100 volt, you move further, this reduces or this increases in this case, right, not reduces. So minus 100 to minus 50 it got increased, right, and then this is minus 25, and at infinity again you are going to get 0. So this is the way potential will be varying as you keep moving away from the charge. So potential due to point charge is given by this expression. This I can use to derive result for other distributions. Let us see. Due to system of charges, like if I keep, this is actually V, so in place of this, this is Vi, right, this is V due to all the charges, it is nothing but sigma, so symbol is not coming correct, this is sigma, okay. So what does that mean, that if I have multiple charges in a space, and let us say this is Q1, this is Q2, this is Q3 and this is Qn, and I want to find out potential somewhere here due to this distribution. As potential is a scalar quantity, I can add all the term. What I can write is potential total is potential produced by first charge, potential produced by second charge, potential produced by third charge, potential produced by nth charge. So everywhere, as these are point charges, I can write kq1 divided by r1, kq2 divided by r2, kqn divided by rn. That can also be written as, if you take k out, sigma qn divided by Rn, right, this sigma is sigma. So I can write the expression this way: if there are multiple charges, potential is a scalar quantity, you can directly add. Field was a vector quantity, that is why we had to add vectorially. Now here you have to just add all scalar quantities. What if our distribution is continuous one? So instead of discrete distribution, if I say charge is distributed on the surface like this, and I am interested in finding potential at this particular point. So what I can do, I can take a small element, first I will get the potential produced by this small element at this particular point and integrate. Directly we can integrate. So because of this dq charge at this distance, what would be the potential? I will write that and I will integrate it. So it can also be written as, this is integration symbol. Right. So integrating contribution of all such elements here will give you total potential produced by the continuous distribution. So depending on whether our distribution is discrete or continuous one, we can use this one or this one, right. So now we are talking about this situation where distributed is the continuous one. So let us take first example. We have a ring and I am interested in finding the potential at this particular point. So every element will contribute, every element on the ring just look at this element which is at distance, this angle will be 90 degree, right. So this will be r square plus small r square. So first I will find the contribution of this element over here, let the charge is dq. So what we can write, potential contribution dV is equal to k dq divided by r separation, right. R is the separation. So I am directly substituting the value. So separation is under root capital R square plus small r square. This if I can integrate, I will get the potential, and you can see that all these terms which are appearing in the expression, these all are constant, only variable is dq. So when I integrate this one, then I need to just integrate the total charge appearing on the ring. So 0 to q will be the total charge. So if you integrate, you will get 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught, integration of this dq is q, and this as it is constant you can directly write same way, right. Here this is, if you are writing x here, then this will be x, and x is the distance of point from center of ring. I can also solve this problem using relation. So I will call it method 1. Right. So using the result of point charge, I am getting the field I am getting the potential created by the ring. I can also use dV is equal to minus E dot dr. I can also use, because I know what is the field produced by ring at some distance r or x. In this case, if it is x, let us write x here. So, due to ring field, electric field due to ring at any general point x, k q x divided by x square plus r square to the power 3 by 2. So, what I can do in method 2, I can substitute the value of field. So, what this formula says and what this formula says, here this dV is the contribution by all the elements on the ring. We are adding all the contribution at this particular point, right. Here dV is not the contribution, it is the difference. So, here this is contribution, while if I am using this one, this is difference. If you go in electric field by distance x, potential get reduced by dV. So, here this is the difference between 2 points. So, from this point, if you move further by dx and you are assuming that potential here is V, and by further moving distance dx, potential reduces to V minus dV. So, that dV what we are writing here is the difference between the potential at this point and this point, right. So, meaning of this one and this one is different, though everywhere I am writing dV only, right. Here it is contribution and here it is difference. Now, if I substitute this value field minus kqx divided by r square plus x square to the power 3 by 2 dx, then here I need to put the limit, because this was the contribution, it gets added and you got the total potential. Here this is not the contribution, it is the difference. So, as you keep moving from here to infinity, potential reduces and it becomes 0. So, reference is at x is equal to infinity, potential is 0. What would be the potential at some distance x? And in previous class I already told how to integrate such type of function. If you multiply and divide by 2, this is t, this will be dt, right. So, it will come in this format, dt divided by t to the power 3 by 2, and integration of this one was 2 divided by under root t. Putting upper limit and lower limit, we can reduce the expression and finally you will get this only, right. So, whether you go by method 1 or method 2, you are going to get the same result, but the meaning of dV we are writing using method 1 . The meaning of dV what we are writing in using method 1 is totally different to the meaning of dV what we are writing in method 2. Method 2 it is saying that it is the difference between 2 points. Method 1 is saying it is a small contribution, that is why we are writing dV, a small contribution in potential by this element at this particular point. In this one already this limit is inculcated. While deriving the result for the point charge, you have already taken potential at infinity to be 0, right. So, in this one already these limits are there. You do not have to again put the limit because these are the contributions of small elements on the ring. So, method 1 or method 2 you are going to get this one. So, similarly for any situation you may go by method 1 or you may go by method 2, it all depends on you what you feel comfortable in, right. Now, let us take another distribution. So, we have taken ring, now we are taking disc. Before that, one point, if I want to plot this variation, you can see as x increases potential decreases. For the least value of x you will get the highest value of potential. So, for x is equal to 0 you are going to get highest potential. So, potential due to ring at the center of ring will be highest, and as you keep moving away along the axis potential keep reducing, right, and at origin the potential is kq divided by capital R if you substitute x is equal to 0 here, right. So, on this axis I am plotting V and on this axis I am plotting x. So, whether you go this side or you go on other side the variation will be symmetric, right. Now, let us see another distribution. Disk. So, we have got a charged disk. Where charge is distributed only on this face. This way charge is distributed and I want to find out the potential due to the whole disk at this particular point, right. Whatever we did to find out electric field produced by disk at that particular point, in the same way we can find out the potential, only thing expression is different. So, we know field produced by ring. So, what I will do, I will take a ring on the surface of the disk. So, I will take element as a ring, I will first find out the contribution due to this ring at that particular point and then I will add all the contributions by rings of different radius, right. So, because of the ring potential at this point, so we know dV is equal to, because the ring will have charge, say something dq. So, just now we have seen the expression is k dq divided by under root, this is x, this is r. So, x square plus r square. So, this is the contribution by this particular ring of radius r and thickness dr. So, thickness of this ring is dr. If I assume surface charge density to be sigma, if surface charge density is sigma, this dq can be written sigma into area of ring. If you cut this ring and open it, it will become something like this. The periphery of the ring is 2 pi r. So, length of this one is 2 pi r, length of this one is 2 pi r and the thickness of the ring what you are considering is dr. So, if I ask what is the area of this one, that is 2 pi r dr. So, sigma into 2 pi r dr. Right. Now, it is not required, I will erase it. So, I hope this point is clear. So, I got the area of the ring multiplied to surface charge density, you will get the charge on this particular ring and this charge I can use here. this charge we can use here. So, if I substitute charge over there, then I will get k 1 upon 4 pi epsilon naught dq sigma into 2 pi r dr divided by under root this, right. Now, number of variable, at a fixed point I want to find out field, at distance x I want to find out field, that is a fixed point, and due to rings of different radii. So, due to ring of different radii, that means r is variable. So, only variable is r, there is only one variable in the expression. I can integrate this one, I can integrate this one. So, taking all the constant out, I can integrate, this is r dr divided by r square plus x square, right. So, this is r dr under root r square plus x square. If I multiply and divide by 2 and integrate this expression alone, then this upper term will become dt if this is t. I hope you are understanding what I am doing. So, I am assuming r square plus x square is equal to t. Here r is variable, x is constant. R is variable, that means 2r dr after differentiation of constant term is 0 dt. So, in place of 2r dr I can write dt, and in place of under root r square plus x square I can substitute t, right. So, after simplification I will get this one, integration of this term. So, t to the power minus t to the power t to the power minus 1 by 2, if you get this term in numerator, after integration you will get 1 divided by minus 1. If you simplify this one, then you will get under root t over here, and this will become plus 1 by 2, that means 2 will come here. So, integration of this expression will give you 2 under root t. And what was t? I hope this part is clear, so I erase all. So, this is nothing but 2 r square plus x square. I substitute the value of t back. Limit will be from 0 to capital R, limit will be of a small r, which is 0 to capital R. So, upper limit minus lower limit if you do, you will get 2 under root capital R square plus x square minus lower limit, if you substitute you will get x. So, basically the integration of this one will be this one, 2, this 2 and that 2 will get cancelled out, this is 1 upon 2 outside, right. So, 1 upon 2 was outside into 1 by 2 into 1 by 2. So, this 2 and 2 will go, and finally you will get without this 2 . So, if I simplify this expression, then what I will get is sigma upon 2 epsilon naught in bracket r square plus x square. So, I hope integration part is clear. Let us see the formula. So, potential at any distance x from the center of disk is given by this expression, right. So, ring over, disk over. Let us move to next distribution. spherical shell. So, we have got a spherical shell where charge is distributed over the surface. So, as charge is distributed over surface, we will be defining surface charge density sigma. Sigma will be equal to whatever be the total charge distributed divided by surface area 4 pi r square. Let the radius of this one is capital R. So, I am interested to find what is the field inside. Field inside at any general point we know, at center 0, at any other point it will be inside, at any other point it is 0. We have proved this one in our field class, right. So, field inside is 0 and we know that if field inside is 0, dV is equal to minus E dot dr. If I say field inside is 0, that means dV is equal to 0, that means potential is equal to constant. It says that everywhere inside potential will be same. And what would be the value? As long as you are not crossing this charge, the potential everywhere will be same. And exactly on the surface, what would be the potential? As this is spherical distribution, it is highly symmetric distribution, uniform distribution, I can consider the whole charge kept at the center to find out the potential at distance r on surface. For any point just outside the surface, somewhere here, I can assume the whole charge is concentrated at center. That means the potential on the surface somewhere here, that will be k q divided by capital R on surface. So, from here to every point inside the hollow sphere, everywhere potential remains constant and that will be equal to the potential on the surface. That means I can write potential inside is same as potential at surface, that is q upon 4 pi epsilon naught capital R. So, irrespective of the point you select inside, everywhere potential will be same because there is no field which can alter the potential inside. And for outside point we know, if I take point outside, somewhere here if I am interested in, then as we are considering potential, as we are considering the whole charge is concentrated at center, the potential outside can be directly written kq divided by r. That means up to the surface, its value is constant and that value is kq divided by capital R, and as you just leave the surface, the potential start decreasing according to 1 upon r. So, as there is no field present inside, potential everywhere will be same, and when you cross this one, then you can assume whole charge is concentrated at center, and from center to distance r, what is the potential you can directly write from the point charge result, kq divided by r, right. So, thin shell is clear. Let us take solid sphere. Solid sphere, there is a field inside and that varies linearly. So, inside field is K capital Q, if I am writing this total charge capital Q and charge is distributed over volume. So, charge is distributed over volume and we know the field at some distance r is in this direction and given by E inside KQ small r divided by r cube, right. Using this result, dV is equal to minus E dot dr. Using this result here, I can get the potential difference. Now, what would be the limit? As we are writing this for any point inside, that means I need to put the limit for any point from center to surface. I do not know what would be the potential at center or any other point except on the surface, because for surface I can say that whole charge is concentrated at center and at distance capital R, I can write potential V is equal to K Q divided by K capital Q, right. K capital Q divided by R. So, I know the potential at surface. I cannot directly jump to infinity, potential at infinity is also 0, but the problem is when you jump to infinity, this expression what you are writing here, that is valid for all the point inside only up to the surface, inside up to the surface. So, there is a restriction that I can put the limit up to surface only, and surface we can easily calculate by assuming whole charge to be at center, right. So, what I can write at distance r, I know the potential, that is K Q divided by R, and what would be the potential at distance r? So, substituting this one here, you can see that this is dr, there is r here, integration will give you r square by 2, right. So, if I put it here, upper limit minus lower limit and then minus sign, if I adjust, right. So, by 2 will make it KQ 1 upon 4 pi epsilon naught as 8. Get this term on other side, you can see r square here, r cube here, if you simplify 1 upon r you will get, and get this term on other side, then it will be coming something like this. So, potential at distance r from center of a sphere is given by this formula, q divided by 4 pi epsilon naught r cube 3 r square minus small r square. This can also be written as k q divided by 2 r cube in bracket 3 r square minus r square. It is easy to remember in this way as compared to this way, k q divided by 2 r cube in bracket 3 r square minus r square. If I substitute r is equal to 0, this is potential at any general point P. If I just substitute r is equal to 0 in this expression, so look at the expression, in the expression if I write r is equal to 0, that means center I am talking about. So, center this quantity will become 0 and this will become kq divided by 2r, this and this will get cancelled out, times 3, this 3 will come in front. look at this one, potential is kq by r on the surface, and at center we are getting 3 by 2 times of the value on the surface, kq divided by r into 3 by 2. That means potential at the center, if I am talking about potential here, so potential at center is 3 by 2 times whatever is coming on the surface, kq divided by r. And how potential is varying inside? You can see v to the power 1 r square, this is a parabolic function, inverted parabola, but this is in the form of y square is equal to 4ax, or I can say x is equal to y square divided by 4a. So this to the power 1 and this to the power 2. In this case y and x are different, right. So I can also write this one x square is equal to 4ay, that means y is equal to x square divided by 4a. This y to the power 1, v to the power 1 x square, that is r square, this is a parabolic function. So inside potential varies parabolically, and you can see that potential decreases from 3 kq divided by 2r, it has become kq divided by r. So inside it will vary parabolically, and outside when you go outside, using the same logic I can write the potential at distance r, whole charge is at center, and you can write k q divided by small r. So outside it is inversely proportional to r, and inside it is following a parabolic relation. So if you draw the variation, look at this one. So potential as a function of r, if I want to plot, then here that is kq divided by r 3 by 2 times, and somewhere here on the surface this is representing r is equal to capital R. On the surface it is kq divided by r, and as you go outside then this potential is inversely proportional to r. So this is very important result. So frequently question comes from solid sphere where we can directly apply this formula and get the result. So remember this formula. Let us go to next distribution. Okay. Before getting into next distribution, let us see one example, a simple example for discrete charge distribution. So we have got 3 charges in space, and question is what is the potential at origin. So first locate all 3 charges, very simple question. Locate the x axis, y axis, z axis. Now if I want to locate all the charges, so first one is placed, that is 1 microcoulomb is placed at 1, 0, 0. So first charge is placed on x axis, this is 1 microcoulomb. One comma 0, 0, and see the next one 0, 2, 0, that means on y axis. So minus 2 microcoulomb is placed at 0, 2, 0, and the last one, that is 3 microcoulomb, which is placed at on x axis, right, at 0, 0, 3. Now question is, due to this discrete charge distribution, what is the potential at this particular point? As potential is a scalar quantity, I can directly write potential produced by first one, second one and third one, and I can add. Now potential produced by first one, that is KQ, KQ I can write, I am just writing Q1, you can substitute the value, divide by R1 plus KQ2 divide by R2 plus KQ3 divided by R3, right. What you have to keep in mind, that charge must be with sign, right. So in place of Q1 I need to write 1 microcoulomb 10 to the power minus 6 coulomb. In place of Q2 I need to write 2 into 10 to the power minus 6 coulomb with minus sign, charge with sign. And the third one it is 3 into 10 to the power 6 coulomb, right. Substitute all the value, you will get the potential at origin. So simple example, potential is a scalar quantity, we have to substitute charge with sign, distances all you know. So from here this is at distance 1, so here I will write 1, this I will write 2 and this I will write 3, right. So simplify, you will get 9 into 10 to the power 9 into 10 to the power 3 volt, right. You can simplify, simple question. Now let us take another distribution. So we have already talked about the field produced by infinitely large wire. So if I ask what is the potential at any general point R, so from here at distance R, if I want to find out potential, right, and charge is linearly distributed, up to infinity, from minus infinity to plus infinity, and I am interested in finding the potential at distance R. You can see from wire at distance R, field will be away from wire, perpendicular to the wire. So for this point, field will be in this direction towards you, that will be perpendicular to the wire and away from wire. And if I am interested in finding the potential difference, then what I can do, I can use dV is equal to minus E dot dr and integrate. Field due to infinite straight wire, at this particular point the field will be in this direction and the value of the field, is 2 lambda upon 4 pi epsilon naught r. This result we have derived because of infinite straight wire at distance r. What would be the field that we have derived, right? So using that result I can write 2 lambda upon 4 pi epsilon naught r dr Now comes limit. As you go dr distance along the field, we know that if potential here is V, the potential here will be V minus dV. If you go along the field by distance dr, potential will get reduced by dV, right. So I can put the limit from position A to say some position B we are going. So from position A I am going to position B, right, away from where I am moving. So potential at A, position at A, position at B, potential at B, position at B. Let us do the integration. So, Vb minus Va will be equal to minus 2 lambda upon 4 pi epsilon naught. This will give you log, natural log, dr by r integration will give you natural log with limit Ra to Rb. So, upper limit minus lower limit, you will get ln Rb minus ln Ra, ln A minus ln B, ln A minus ln B will be ln Rb minus Ra, sorry Rb by Ra. So, integration of this term will give you log upper limit minus lower limit. If you simplify, then you will get ln Rb divided by Ra. This is the expression of potential difference at 2 point from the wire, right. So, if I ask what is the potential difference between point A and point B, this is the expression, and using this expression you can tell the potential difference. Just substitute the value of position at A and position at B. So, values will be given like from wire at 2 centimeter and from wire at 5 centimeter, what is the potential difference. So, just plug in 2 and 5 centimeter here, you will get the potential difference. So, I hope procedure is clear. So, to get the field, instead of taking all the element and integrating, which looks little complicated, I already know the field at distance r. Using the expression, if I integrate, then I will directly get the result. Very simple. Now, let us move to next one, infinite sheet, right. So, here we have got infinite sheet, it is extended up to infinity. So, say this side we have charge, so because of these charges there will be field perpendicular to the plane. So, from plane, if charge is positive, lines will be originating and going till infinity, and the gap between lines will remain same. So, distribution will be uniform. Now, if I ask what is the potential difference between 2 points, say somewhere here and take another point somewhere here. Let this point be at distance x1 and this second point is at distance x2. So, if I ask what is the potential difference between two points, right, because in previous case and this case, look at this one. The problem here was I cannot consider potential at infinity to be 0 because the distribution is going till infinity, right. So, I cannot calculate the absolute value of potential at B by assuming that potential at infinity to be 0. I can talk about the potential difference, right. So, whenever distribution is going till infinity, we cannot take the reference potential at infinity to be 0, right. You can talk about the potential difference between 2 points. Same thing happens here. I cannot assume that potential at infinity to be 0, that is why I am calculating the potential difference between 2 points in front of infinite sheet. So, I hope this diagram is clear, like this is infinite sheet and in front of it field lines will be there and going till infinity, field will be uniform. Or in 3 dimension if you want to see, look at this one. So, let us say this is x axis, this is y axis and this is z axis coming towards you and field lines will be like this, right. So, question is what is the potential difference? So, again I can use the same, dV is equal to minus E dot dr, integrate, and this E we know, electric field in front of infinite sheet, sigma upon 2 epsilon naught. So, if I substitute that one, sigma upon 2 epsilon naught, I will get this way. Now, at x1 if potential is V1 and at x2 if potential is V2, and I simplify this one, then I will get V2 minus V1 is equal to minus sigma upon 2 epsilon naught in bracket x2 minus x1. So, this is the way we write the potential difference between 2 points in front of infinite sheet, right. Let us see one example based on the what we have just discussed. So, we have got one infinite state wire of linear charge density lambda, and question is we need to move q naught, charge from point A to point B. For that, how much work is done by external agent? How much work will be required by the external agent? So, we can use the basic definition work done by external agent changes the potential energy of the system, provided this is being done without any change in kinetic energy, right. We already discussed this point. So, without any change in kinetic energy, if I am moving particle, whatever work I am doing, that changes the potential energy of the system, and from potential energy and potential expression we know that the potential energy, if you multiply, see the way we defined potential difference is equal to change in the potential energy when test charge is being moved, right, per unit test charge. So, this can be written potential difference into q naught. So, q naught if I multiply to the potential difference created by this infinite straight wire, then I will get the work done by external agent. I hope this point is clear, right. So, to substitute this term, I can write q naught into potential difference created by the straight wire at these two locations. No potential difference, just now we have seen dV is equal to minus E dot dr because of the straight wire. This can be written 2 lambda 4 pi epsilon naught r dr minus sign dV. Let us put limit. So, here I need to write potential final minus potential initial, right. So, this is V B minus VA final minus initial VB minus VA. So, I will put limit accordingly, VB here, VA here, and when at B the particle is at distance 2r. When it was at A, particle was at distance 3r. So, here I will add 3r. So, when you integrate this one, you will get log upper limit minus lower limit with minus sign. So, lower minus upper it will become. So, if I just simplify, what I can see is VB minus VA is coming VA minus VB is coming 2 lambda upon 4 pi epsilon naught ln 3 by 2. I hope you are understanding. This will become log A minus log B, that can be written log A by B. As minus sign is there, you have to reverse. After reversing, you will get this, right. So, this is just potential difference. So, remember this one. I will erase this part. So, I will substitute this value here. So, work done by external will become charge times potential difference, and potential difference is, we just calculated, 2 lambda upon 4 pi epsilon naught ln 3 by 2. Final minus initial, change in potential, final minus initial. So, substitute the value here, potential difference here, multiplied to Q naught, you will get the work done by external agent. Here we are slowly moving the charged particles. Slowly as I move, you can see that obviously field is perpendicular to the wire, away from wire like this, then we need to exert force opposite to the field. So, to move the particle we are doing a positive work. So, this quantity is coming positive because we are doing a positive work. Now, let us understand next concept, equipotential surface. So, if we have got a positive charge, and we know the potential due to positive charge is given by V is equal to KQ by R. So, everywhere from point charge, potential is V only, right. So, if I put potential constant, then I will get, if I want to draw it on 2-dimensional plane, then I will get concentric circles. For example, if I fix the value of this one constant, for example, I want potential to be 10 volt. So, for 10 volt you will get, because these values are constant, you are getting circle of particular radius. Similarly, if I make it to 100 volt, then obviously radius will be somewhat different for that particular potential. So, as you move away from charge, potential keep decreasing, right. So, this is representing, this circle is representing potential of a particular value. You change the value, you will get another circle. As you keep going out, all these circles will be having lesser value as compared to the circles near to the positive charge, right. So, in 3 dimension, if I take charge in 3 dimension, these all charges will have spherical equipotential surface. On 2 dimension, you can see they are circles. Let us see it again. So, I want to draw equipotential lines. So, for a particular value of potential, I am getting circles. So, this one circle represent a particular value, this circle represent the particular value, another circle will represent another value. As you keep moving away, the potential of circle at infinity will be 0, So, potential at infinity will be 0, right. So, all these equipotential surfaces will be spherical and concentric. This is 2-dimensional diagram, that is why you are seeing circles. In 3 dimension it will be sphere. So, our equipotential surfaces will be spherical. So, this one, they all are representing equipotential surface. You can observe one point that these field lines are making 90 degree with equipotential surface. Field lines at every point making 90 degree with equipotential surface. So, if we got positive charge, then field lines will be outward, and when you are going away from the charge, potential, equipotential surface potential keep reducing, right. If I have negative charge instead of positive charge, field lines will be inward. If field lines are inward, then equipotential spherical surface, as you move from charge to infinity, the potential increases. So, somewhere here it will have negative potential, and as you keep going at infinity it will again have 0 potential, then potential is increasing. So, equipotential lines will be, if I talk about its projection on 2 dimension, these will be line, and in this case it is circle. If I talk what is happening in 3 dimension, those will be spherical. Now, let us see next distribution. I hope this point is clear. Because of the point charge, you have got spherical equipotential surfaces. Now, if I take infinite charge, then I will get equipotential surface as cylinder, concentric cylinders, right. So, for example, see, if I write Vb minus Va, then we got minus Ln, sorry, this is two lambda upon 4 pi epsilon naught Ln Rb minus Ra. Keeping fixed position for fixed potential, if I make this fixed, then you can see at particular distance from this infinite wire, you are going to get same potential. So, from wire at fixed distance r, you are going to get same potential. If you join all these points, then you will get cylinder. So, for infinite straight wire you will get cylindrical equipotential surface. Now, let us see another one. So, cylindrical equipotential surface. Let us see another distribution. What if I take uniform field? It might be created by infinite sheet. If field lines are say along x axis and distribution is uniform. So, this is uniform field, and because of the uniform field in a space you will get equipotential surface as plane. Again you can see that the angle made by these lines with the equipotential surface is 90 degree at every point. Right. So, if I take point charge, I will get spherical equipotential surface. If I take infinite straight wire, then I will get cylindrical equipotential surface. If I take uniform field, that might be created by just now we have seen, that might be created by some infinite sheet, So, in front of this infinite sheet there will be equipotential surfaces like plane, and as you go along the direction of field, potential decreases. So, V1 is greater than V2 is greater than V3, right. So, these are the three basic type of equipotential surfaces we have. It can be spherical, it can be cylindrical, and it can be planar, right. So, the concept of equipotential surface is clear. In our next class, we will talk more about equipotential surfaces, and we will take up different distribution to locate the equipotential surface in space. So, I hope you understood today's class and you enjoyed the class. Thanks for watching.